We left off here. Are there any questions about last day's assignment?
Number 5 and number 8.
Yeah, 172. Okay, 5 and 8. Anybody else? Compared to math, there's relatively few notes today, so shouldn't be a problem going over some questions. Okay, 5 and 8. I'll have a look at them. All right. So this is on page 173. Numero cinco. Says you're dragging a 110 kilogram trunk across floor at a constant velocity with a horizontal force 480 newtons. Okay, calculate the coefficient of kinetic friction. So your force is, okay, so it's mu k equals fk over fn. All right, so your applied force, constant velocity, so acceleration is 0. So calculate coefficient of friction. So I think it'll just be 380 110 times 9.8. Do you have the answer handy, Nathan, so I don't have to look it up?
I think it's 0.35.
That's what I got. Was it A, B, or C specifically, or?
Mostly C, but also B.
Okay. So that's A. B says, a friend decides to help you by pulling on the trunk with a force of 150 newtons up. Will this help? Yes. Calculate the force required to pull the trunk at a constant velocity to help you decide. Okay. So first of all, the way this works, so it's a 110 kilogram trunk, okay? So mass equals 110 kilograms. The weight, which is different from the mass, is 110 times 9.8. Divided by equals 1078, 1078. So what your friend, oh no, hang on. This is the amount of force that the earth is pulling this trunk to the ground with. So the applied force from your friend, are they a friend? Yeah, they're a friend, is 150 newtons up, which means effectively the net weight of this trunk is 1078 minus 150. Does that make sense? That's why it's making it easier?
Yeah. Yeah, that helps.
Oh, 78 minus 150. So because they're effectively making the trunk lighter. Part C, instead of pulling on the trunk, your 55 kilogram friend just sits on it because that's what they're like. So the mass is now 110 plus, or the net mass, if you will, 110 plus 55 equals 165. So the new normal force is 165 times gravity, which is 9.8. $16, $17. So that's not kind of finishing the whole question, but it's telling you that the normal force, it used to be 110 times 9.8. Now it's 165 times 9.8. That's where the big change happens. Yeah, I meant net, but it's also the net, the normal force. Does that give you enough? You want me to keep going?
For B, I was just confused with like how to calculate the the constant velocity, like the force, what would you calculate there?
So the first question asked us to figure out this coefficient of friction here. So we would use that. So it'd be mu k equals Fk over Fn. And so mu k is 0.35.
Oh, yeah, now I see it.
Yeah, you're good?
Yeah.
Okay, jump into 8.
Hold on half a second.
Okay. B and C are the same idea. It's just the normal force.
Yeah. Okay. Yeah, you can go to 8 now. I'm good.
All for the force of friction. So numero 8. I just thought of something. Says a gradually increasing horizontal force is applied to an object initially at rest on a horizontal surface. So something is just being pushed, so like the force is increasing. Oh, here, just for fun, let's pretend I have a water bottle. And so you're pushing, 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 and eventually it's gonna move. Draw a graph of the force of friction versus the applied force in each situation. Oh, okay. The coefficient of static friction is slightly greater. The coefficient of static friction is equal. Okay, so here, let me just turn instead of me drawing because of my poor drawing habits. Bottom of page 168. This would be your answer for part A. Part B is if kinetic friction is at the same as Fs max.
Okay, thanks.
Does that make sense?
Yeah. I think it was actually 9 that I was confused with.
Oh, okay.
I accidentally circled 8.
Way to go. Way to go. That's -1 off your next test. Number 9, a door stop keeps a door open when it is wedged underneath the door. Use the concepts from the section to explain how the door stop works. There's all kinds of friction going on there. When you have a door stop, why does my camera keep moving? So, you're gonna make me draw this, hey? Okay, so. Oh, that's terrible. Okay, whatever, there's a door stop. The thing is, when a door comes down on it, oh, why are you making me draw stuff, man? So this is the door, and it kind of swings both ways. When the door wedges in there, essentially a doorstop gets stuck. Not only is it kind of sliding on the floor, like if this is covered in silk on the bottom, it's a crappy doorstop. It's not going to work. It's just going to slide out of the way. Wood gives enough friction, not only because it stops it from sliding, but also because it wedges in the door. You'll see sometimes people will put their foot against the end here and pull the door to the doorstop. And what it does is it forces this underneath, because otherwise the door might just push this out of the way. But when the doorstop is wedged underneath, it's wildly increasing the normal force on the doorstop, because then it's pushing down way harder. But also, it's lifting this door. So when the door, like, I don't know if you've ever taken a door off of the jambs before, like it kind of connects. It's got these things. And the door kind of does whatever this, and then yeah, it looks like a book. Anyways, my point is, when the wedge is wedged underneath the door, this whole thing kind of wrenches up a little bit, and it causes all kinds of friction in these spots as well. Like a door, when it's hung properly, it swings nice, open and close. But you notice some doors, maybe in your house or cabin or somewhere else you've ever been, like you got to kind of lift up on them a little bit because they're sagging or whatever. And so that's causing friction. Well, if you lift up, it also doesn't turn as nicely as it should on these things. So there's tons of friction everywhere, but a big part of it is wedging on top of this wedge, and it increases the force going down. If you put this thing on a scale, it's almost weightless. If you still have it on a scale and this door is wedged over top of it, now you've added kind of like the equivalent of 100 kilograms or more.
Okay, yeah, that makes sense. Thank
Does that
you.
make sense? Like, in all honesty, I wouldn't ask you, I don't ever want to be just, oh, this is a test question. This is not a test question. I don't want you guys to learn that way. But I will say, like, how would you mark this on a test question? So it's not something that you would have to be able to break down super clearly, but you should have an understanding of it. And let's be honest, these aren't the worst drawings you've ever seen in your life. I'm actually kind of okay with them. Was that good for you though, for number 9?
Yeah.
Anybody else? Any other questions? All right, let's do a little notes. Just a little though. No, I won't be able to see your thumbs up without me blocking the screen here, so I'll just ask in a few moments if people are done. These Fs at the very bottom, Fnet, Fa, Fk, they should all have vectors over top. Oh wait, I can see everybody, so give me a thumbs up when you're done writing, please. Kate, what happened to the big brain? It's a secret, I guess. Thank you, Ryan. Thank you, Matthew. Thank you again, Kate. Still don't know where your big brain is. Thank you, Nathan. I can't think of what it's called. Not your emoji. What do you call it? Doesn't matter. Clearly, Kate's not talking to me today. That's okay. That's okay. All right, static friction must be overcome for motion to occur. I've talked about this lots. Like when I'm pushing at my desk or something, it's kind of stuck, and then it gives way. More than one object is attached or connected. The combined maximum force of static friction must be overcome. If I am pulling a chain of desks, and there's a row of you guys, and you're holding onto the desk in front of you, each of you has a different mass. You're going to have a different, provided all the bottoms of the chairs are the same, you're going to have a different frictional force. Have to add those all up if I want to pull you all at one shot. Static friction is also necessary for movement. Imagine walking on ice without any friction. This is why I have studded tires on my bike for the winter, because I need static friction to help me kind of roll my way through life. Kinetic friction acts on a moving object in the opposite direction of motion. So consider figure 8 on page 175. So I just wanted you to look at this because I think it's kind of interesting. So I got to stop sharing my screen then. Oh, somebody's chatting. Is that Kate saying I can't talk right now? Different. Okay. I hate having to make the screen big all the time. Okay, so now if we're looking at this here, I think this is kind of cool because look at this part A. It says both the applied force and friction act in the same direction. And you have to think, well, what would make that happen? Imagine, I think the description is giving here, you've got a box that's sliding towards you for some reason, had some big force and it's slowing down, but it's heading towards you. Kinetic friction is working on it, but you put out your hands to stop it and you start applying force to slow it down as well. That's when kinetic friction is another example of when kinetic friction can work with you. But it's usually in the opposite of what you're trying to do. So, here you're just trying to drag something and kinetic friction's like, I don't want to go. It never wants to go. That's kinetic friction for you. All right. All right, back to sharing the screen. Give me a thumbs up when you're done, pretty please. Thank you, Ryan. Thank you, Kate. Thank you, Matthew. I'm confused. Did Nathan, Ryan, did you already push the thumbs up? That's how ADD works in real life. I forget things the moment after they're done. Okay, beautiful. So let's do some of this work. Why do I have to keep making this full screen? So there's lots, as it kind of says in the notes there are lots of kind of tutorial and practice questions. There are 3 tutorials in this relatively short lesson. I would encourage you to look through them. But in each tutorial, there's at least 2 practice questions, which would take a long time. So tutorial 1, there's practice 1 or 2. Number 2 has a pulley system. Should we do 2? That'll be harder. Yes, yes, we should. So this is number 2 from page 174. A 4 kilogram block of wood rests on a table, sits on a table. A string is tied to the wood, running over a pulley and down to a hanging object. The greatest mass that can be hung from the string without moving the block of wood is 1.8 kilograms. Calculate the coefficient of static friction between the block of wood and the table. Okay, so the hanging, so for those of you who maybe don't have it in front of you, it looks like this. Well, clearly not exactly because I'm not an artist, okay? This is 4 kilograms. This is 1.8. So the applied force that's trying to pull this 4 kilogram block is mass times gravity. So equals mass of 1.8 times gravity of 9.8, which we all know 1.8 times 9.8 is 17.64. 17.64 newtons. What's the actual question asking? Calculate the coefficient of static friction. Okay, so mu S equals Fs over Fn. equals force of static friction. This is the max right here, like 0.64, literally. If it was 0.65, it should start moving. So Fs max 17.64 over the normal force, which is 4 times 9.8. Well, 9.8, so that's 19.6, that's 38, so that's 39.2. Should I have written that in? That's 4 times 9.8. Okay, that's normal force, mass times gravity. And now I'm going to check the math because I'm worried I did it wrong. 9.8 times 4. No, it's good. So this is going to give me our coefficient of static friction, 17.64 divided by 39.2, 0.45. That is the coefficient of static friction. I'm getting better at these drawings. You have to admit it, whether you like it or not. Any problems with that? Anybody need more time to copy it down? I wonder if it's better if while I'm doing the work, you just listen. I guess it's up to you, but just don't write anything down. Just follow. And then when it's down, then you can write it down. As you're writing it down, you know what you're looking for and you know what you're doing, and you can add your own little notes. Just a thought, especially over Zoom. All right. Next tutorial practice, page 175. 1 or 2, is there a preference? 1 looks a little longer. I'm going to do 2 just because it's probably harder, just because it's number 2. 2 on page 175. A skater with a mass of 58 kilograms is holding one end of a rope and standing at rest on ice. Assume no friction. Another person with a mass of 78 is standing just off the ice and level ground, is holding the other end of the rope. Person standing on the ground, pulls on the rope to accelerate the skater forward. The coefficient of static friction between the ground and the off-ice person is 0.65. Calculate the maximum possible acceleration of the skater. Okay, I'm very much a visual learner, so I will, even though I'm a terrible artist, I'll draw these things out to make sure I know what I'm doing. This person is 78. So this is ice. This is carpet. I don't know, doesn't matter, rubber or something. Coefficient of static friction here was given to us, wasn't it? 0.65. Calculate the maximum possible acceleration. What does it depend on? Oh, okay, so they don't want to slip. This person doesn't want to slip. That's what's going to say how hard they can pull that rope with. So mu s equals Fs max over Fn. So what's the maximum amount of force? This is what we're going to solve for. What's the maximum amount of force that they can pull with? 0.65 equals, I'm going to figure out what that is. And then normal force is 78 times 9.8, which means 0.65 times 78 times 9.8 is going to give us our maximum force here. 0.65 times 78 times 9.8 equals 496.86. 496.86, 500 almost. But because this isn't a final answer, I'm not going to round anything yet. What's the question? How fast? Maximum possible acceleration. Okay, so the force that this person's applying to 58 kilogram friend here is 496.86. F equals ma. There's no friction here. Force is 496.86. 496.86 equals mass 58 times a. So divide both sides by 58. Why did I clear the screen? 496.86 divided by 58. 8.6. Acceleration equals 8.6 meters per second squared. And we're going to say to the right. Does it say left, right? The person standing just off the ice. Doesn't say the direction. Oh, it says towards off ice person, so whatever. Forward. That works. Any problems? Anyone still writing this down? We're all good. Take it away. All right, this is great. Talking to myself. All right, we've got one more example, I think. Or do we? Maybe if nobody says nothing. We have 4 questions to choose from here, my friends. Any preference? 1, 2, 3, or 4? It looks like question number 1 is, oh, excuse me. Question number 1 is kind of a 5 kinematics equations questions where you got to solve for final displacement and stuff. So I'm not going to do it. 2, snowmobiles pulling sleds. Calculate the acceleration of a snowmobile sled. Let's do number 2. So this is 2 on page 177. The snowmobile is used to pull 2 sleds across the ice. The mass of the snowmobile and the rider is 320. So 320. Pulling 2 other sleds. The mass of the first sled behind the snowmobile is 120. And the mass of the second is 140. The ground exerts a force of 1,500 newtons forward on the snowmobile. So I'm going to say the applied force equals 1,500. And if you're wondering, like that sounds weird, like the ground exerts a force 1,500 newtons forward. Well, there's on a snowmobile, there's these tracks and it's turning and not slipping. So it's moving forward. It's turning this way. And if it's not slipping, then it's pushing along the ground and the ground is pushing back. Same way you do when you walk. Provided you're not slipping, you are pushing on the ground, and the ground's pushing you forward. So the applied force, 1,500 newtons forward. The coefficient of kinetic friction for the sleds on ice is 0.15. So mu k equals 0.15. Mu k equals 0.15. Assume that no other frictional forces act on the snowmobile and calculate the acceleration of snowmobile and sleds. All right. So here, what we're going to do here, I'll tell you right now, we have 1,500 newtons is being pumped through this track here. 1,500 newtons is pulling this way, but we have friction on each of these. There's friction that's pushing this way and friction that's pushing this way. So we need to find out the net force. Remember, F net is applied plus friction. Friction's in the opposite direction, so it's essentially you're subtracting it. Figure out what these 2 forces of friction are, combine it with this, and then we've got F equals MA. All right, so I'm just going to do it right under here. So mu k equals Fk. We want to find out the force of friction over 140 times 9.8. This is the normal force under here, and mu k equals 0.15. So 0.15 times 140 times 9.8 is going to be Fk of, let's say sled. Actually, I think this is sled 2. So we'll say sled 2. So 0.15 times 140 times 9.8, 205.8. 205.8 newtons. And so this is going to go backwards. This is going to go forwards. So over here, same idea, 0.15 equals Fk, but that's Fk1 over 120 times 9.8. Fk1 is 0.15 times 120 times 9.8, 176.4, 176.4 newtons backwards. Have a quick look to see this is lighter. Same coefficient of friction, so the friction should be smaller, 176, 205. Yes, looks good to me. Any questions? So F net equals FA plus FK. Arrow, vector, vector. I usually write them right at the end because it's just extra. So anyways, the applied force is 1,500 newtons plus two negative forces, 205.8 plus 176.4. 1,500 minus 205.8 minus 176.4, 1117.8. That's the net force. Newtons forward. F equals ma. 1117.8 equals total mass 320 and 120, so that's 440, 480, 580, so it's 580 times A. Divide both sides by 580 to get your acceleration. Divided by 580, it's 1.9 meters per second squared. 4 to the word. Let me check my answer and I'll be completely off. Nope, it's good. Questions? Too fast? Were you able to see all the sheet that you needed to? Do you need me to move it up or down or anything? Do you need me to not do this while you're finishing? This could be a prank. Like there's nobody writing on either on any of those devices. You guys are just recording this and playing video games and mocking me because you're all muted. Is he getting balder? I think he's getting balder. Yeah, now my watch is shaming me for sitting down. It says, how about a walk? What's this about? Kate said I'm not strong enough. So Nathan. Nobody's saying anything. You guys can go when you're done. You have the assignment. That's the only communication I suppose. Okay. Just like that. Wow.